Hello. So today I have this routed network and everything on this network is great. I've got my routing protocols configured, they're managing the traffic, all links are up and running, redundant traffic flows, everything about this network is great. Now what happens if I want to change out these routers for switches with this same design? And wait a minute, one of my lights went orange and actually now I have a down link. So something just went onto my switch network and shut down one of the links. But in doing so, it's actually saved my network. Hi, I'm Rich. Welcome to the Rich Tech Guy channel. And today we're going to dive into Spanning Tree, what it is, how it works, and how it actually saves your switch networks by taking links down. So let's start by talking about the differences between Layer 3 and Layer 2 networking. Now in the routed network, we're utilizing Layer 3. And why is it able to have fully redundant links versus the Layer 2 switch network, which cannot? And this has to do with loop possibilities and loop mitigation. The Layer 3 network utilizes IP protocols, which has a couple of mechanisms in order to prevent traffic from being caught in a loop and soaking up your bandwidth. The first is through the routing protocols, which find an optimal path for your traffic and then direct the IP packets down that path. Now, if the routing protocols fail and the packets are going back and forth in a loop without any movement towards their destination, the IP protocol has something in its header field called a time to live field. And so at some point, the packet will literally die. The time to live field will count down by 1 every time a router receives the packet. And when that time to live field reaches 0, it drops the packet. Alright, I got a new packet here. Okay, let's check the fields. We got source, we got destination, time to live. Let's reduce it to 1. Oh, it's reached 0. I have no more use for you. Alright, next packet, next packet. Now you can see the time to live field when you do a ping. So for example, I'm going to ping Google. And when I ping Google, I get a time to live field of 117. Now, this is assuming that we're starting at 255 because the time to live field is 8 bits. So 2 to the power of 8 is 256 because computers start counting at 0 with binary counting. Therefore, the maximum value is 255. So that means that for getting Google with a 117 as the value of the time to live field, that means it took 138 hops in order to get to its destination. Now, let's say I ping the South Korean equivalent of Google and I'm based in the US. Now, this time, the time to live field is going to be is only going to be 53. And that means that it's 202 hops for me to get from where I am in the US out to South Korea. Kind of makes sense, but does it really? Let's go to another part of the world. Let's ping the Russian equivalent to Google, which would be Yandex. So when I ping them, the time to live field is 239, which means it only took 16 hops for me in the US to get to the Yandex server. Now what this means is that either the Russians with Yandex have placed a server in the United States and it is closer to me than Google's server, or somewhere along the line I have an optimal routing path with a direct link out to Eastern Europe or possibly even straight into Russia. And that is considerably shortening the number of hops I have to make. So what does the switch network do in terms of mitigating this? Well, nothing. On the Layer 2 Ethernet protocols, there is no time to live field. And this gets complicated even more by the fact that packets, or frames as they are in Layer 2, are more likely to get caught in a loop when you have redundant links. And this is one of the ways that this happens is if a switch doesn't know where to send it, because instead of using routing protocols, the switch just has its own table of local MAC addresses to decide where to send the packet. So if it doesn't know where this particular frame is supposed to go, then what it does is it just sends it out of every interface except for the interface that it came from. All right, we got a new frame here. Let's check that against my table here. Where's this gonna go? Oh, I don't have a match here. Okay, you know what? You get a frame, and you get a frame, and you get a frame, and everybody gets a frame. Oh, no, not you. You gave me the original frame. You're not getting anything. Also, if a switch receives a frame that has a broadcast MAC address, which is all ones in the MAC address, and is resembled as FF, then the switch does the exact same thing as an unknown unicast packet, where it sends the frame out every interface except for the one it received the frame on. All right, new frame coming in. Let's check. Where are you going? Destination is FF. All right, it's a broadcast frame. All right, you get a frame, and you get a frame, and you get a frame, and everybody gets a frame. And oh no, you don't get a frame. You gave me the original one. You don't get anything. So if you have a loop in your switch network, it's very easy to get what's called a broadcast storm, where the frames are just simply going around and around and clogging up the bandwidth for any other traffic. This is where spanning tree comes in to save your network and essentially save the day for you. Now what spanning tree does is it looks for loops in your network, and the way it goes about doing that is through a packet, a particular type of frame called a Bridge Protocol Data Unit, or a BPDU for short. Now, when you connect any device or other switch into a switch connection, the switch will actually bring the interface down initially, and it will put it in what's called a listening state and then into a learning state. During this time, it will listen and look for BPDUs while sending out its own. And at that point, if after a certain amount of time has elapsed and no BPDUs are received, then what it essentially does is it decides there is an end device attached to the network. It's not another switch, so it can safely open up that interface and pass data traffic. On the other hand, if during the listening and learning periods it receives a BPDU from another switch, it then has to start deciding what is going to be the root switch on the network. And to do that, it begins processing and comparing the BPDUs that it does receive. And all of the switches on the network get together and they hold an election utilizing something called a bridge ID, or BID for short. Now the bridge ID is comprised of a particular number, which by default is 32,768, and then it is combined with the MAC address. The switch with the lowest bridge ID wins. Now that means that if all the switches are at default, then the switch with the lowest MAC address wins the election and becomes the root switch. This typically means that it is the oldest switch that becomes the root. There are ways you can manipulate this. The range for the bridge ID can be anywhere from 0 to 65,535. And you can set it in increments of 4096. So you can actually go into your switch, and if you want a particular switch to be the root switch, you can drop it all the way down to 0, then that will define that as the root. So once the switches have determined which one will be the root switch on the network, they then begin to look for any redundant or loop paths to root. So when you are looking at it from the standpoint of the root switch, what it will do is the root switch will open up all of its interfaces and begin passing data traffic. For switches that are not the root, what they will do is they will check their cost paths on the interface and determine which one is the lowest cost path to root. So if a switch then determines that it has more than one path to root by looking at the BPDU data from all the switches, It will then identify the lowest cost path, and it will designate that particular interface as the root interface. That interface will then be opened up and allow data traffic to pass. For any other interfaces, the switch will then determine, first of all, is there a path to root on that interface, or is this going to another switch but does not have a path back to the root switch. In the case where the interface does not have a path back to the root switch, it will open up the interface and allow data to flow on that, and it will classify that as a designated interface. However, if the switch finds that a particular interface goes to another switch, which also has a path back to root, then it will block that interface and it will place it in a blocking state. Now, during blocking state, it will still listen for BPDUs in the event that a particular link goes down or a new optimal path to root is discovered, and then it will realign its interfaces as to whether or not which ones are going to be passing traffic. So let's take a look at this in practice on a lab environment I have. I've got this lab set up here with this particular diagram where I have 4 switches all connected in this manner, which is typical of a access layer distribution layer. And we're going to go on to these switches and take a look at what the output is regarding spanning tree and identify where the block links are, and then also play around with it and set another switch's root and see what happens to the blocked links. Okay, so let's take a look at what's going on the switches when we're logged in and viewing their actual output in regards to spanning tree. So first, we're going to go into switch 0. And on this switch, I am going to run the show spanning tree. And I have multiple VLANs on here. Now, originally, spanning tree did not specify a particular VLAN. It just operated across all of them. Cisco switches adopted the model of per VLAN spanning tree, and that is largely the norm. So I'm going to look at VLAN 200 on these switches. So I'm going to do a show spanning tree VLAN 200. Now what we see here is the switch 0 is the root switch, and its priority is set to the default 32968. So based off of that, we can assume that it has a lower MAC address than the other switches, and therefore that is why it is the root switch. Now the other thing we can do to check, other than it saying that this bridge is the root, but by seeing that every interface is in a designated state and also in a forwarding state, that is another sign that this is the root switch. So if we were on another switch, like let's go to switch 1, so on switch 1, now it's not indicating that this switch is the root. Instead, I'm getting a cost number here. I am showing the default priority, so again, we're going off of lowest MAC address in these switches in the lab. And in the role of the interfaces, the port channel from switch 1 going back to switch 0 is in fact in a root, it's a root port role. Now all the interfaces are forwarding, so this switch has determined that there is no need to block any interfaces. When we expand our check further onto, let's go to switch 2, here we've got the two interfaces, the gigabit Ethernet 00 and 01. 00 is pointing back towards switch 0, and that one is the root interface, which is forwarding. The gigabit Ethernet 01, which is headed towards switch 1, is a suboptimal path to root. So as a result of that, it is blocking that interface. Now, if we go take a look at the last switch in the network, on this one, we have gigabit Ethernet 00, which is pointing towards switch 1. It's the suboptimal path, and so it has a role where it is blocking the traffic, and it is selecting the optimal path to root, which is its root interface on gigabit 01. Now, were gigabit 01 to go down, that would change. So one of the ways we could take a look at this is if I went into the config, and at this point I wanted to go to the interface 01, and I shut the interface down. Now the interface is shut down, and if I do a check on the spanning tree, I only have one interface, the gigabit Ethernet 00 interface, and that is now in a root forwarding state. So when I no shut the interface, so what's going to happen here is when I go in here, again, everything has righted itself. Gigabit Ethernet 01 was once again determined to be the root path, and as a result of that, everything is going to go through that interface, and gigabit Ethernet 00 is back into a blocking state. So let's say I change the switch. I wanted switch 1 to be the root switch. So again, I'm going to go into the configuration, and this time I want to say spanning tree Vlan 200. Now there's a couple ways I could go about doing this. I could actually say set it as the root primary switch, and when it does that, what happens is it has dropped the priority down to 24/776, which what's rather interesting is you could actually go in and manually set another switch to a lower priority and make that switch the root. But essentially what it did though was it dropped it below everything else, and at this point if I were to go on to switch 1 or switch 0 and repeat the spanning tree command, this switch is no longer the root. It now has a root interface going to 00, or going over across the port channel over to switch 1. On switch 2, if I recheck spanning tree, now the gigabit Ethernet interface going to switch 0 is blocked, as that is the suboptimal path to root. The new root, switch 1, has the optimal path through gigabit 01, and we see the same thing happen on switch 3. So when I go back in here, I can take that roll away. And with that, it is still showing itself as the root switch. So I'm going to go on to switch 0, and I really want to make this switch the root. So I even want to make it so that its priority is lower than everybody else out there. So what I'm going to do here is on Vlan 200, I'm going to set, instead of saying root primary, I'm going to set the priority and I'm going to drop it all the way down to 0. So I have made this switch to the root. Now it's actually dropped the priority down to 0, but it's leaving this little note about, it's still going to go ahead and bump it up to 200 on me. But essentially at this point I have set this down so low that the only way another switch could possibly become the root switch is if that other switch also has the priority knocked all the way down and it has a lower MAC address than the other switch. And in doing so, this effectively dictates now that switch 0 is the primary switch in my infrastructure. Now we've only just hit the beginning of spanning tree. There's a lot more content around spanning tree and different types of spanning tree, which I can go into on a future video. But if you like this content, hit the like button, hit subscribe, and join me for more content like this as we go down a technical journey here on the Rich Tech Guy channel. Thank you very much.